There are two reactions involving diols that we want to be aware of. One is the oxidative addition of a pair of alcohol groups using OSO4, which converts an alkene into a diol. So this is our diol forming reaction. The other is the oxidative cleavage of a diol using HiO4, and that works only on specific diols but gives us a pair of carbonyl compounds. And if we look specifically at how this works, our alkene reacts with osmium tetroxide, and there are typically other reagents involved here as well. It's not unusual to see peroxy-tert-butyl alcohol with tert-butyl alcohol or other materials present as supporting reagents and solvents, but our main concern and the only thing that we need to worry about drawing if you want to fill in a reagent is the osmium tetroxide. What this does for us is to break the carbon-carbon pi bond and to add a pair of alcohol groups, one to each carbon. This is a concerted reaction, which means that it's a syn addition. In terms of stereochemistry, the two OHs will end up cis to each other in any example where stereochemistry is observable. The oxidative cleavage, in contrast, takes a diol, like the one that we just produced, and it has to be a 1,2 or vicinal diol. So the two OH groups have to be adjacent, and they can't be pointing in wildly different directions. They were going to use periodic acid, HiO4, which, if we were to look at the mechanism, it would involve an intermediate in which the HiO4 connects to both oxygens, which is why they have to be adjacent and close enough that they can both attach to the iodine. And what we observe is oxidative cleavage of that diol to produce a pair of carbonyl compounds. Similar to ozonolysis. And in fact, if we consider the ozonolysis reaction, note that it's essentially this process in a single step. So we start with the alkene, we use ozone followed by a reductive workup, dimethyl sulfide or zinc with hydrochloric acid, and we cleave that alkene, replacing the double bond on the alkene with the double bond to both carbons of the alkene with carbonyls. And so depending on what's present on the original carbons, we could produce ketones and or aldehydes. So we're not going to do this as a two-step process, but we do now have a means of making a diol. And the HiO4 with a diol is not one that we frequently do for synthetic purposes, but rather it was a means, or is a means, of chemically identifying a vicinal or a 1,2 diol, where the two OHs are on carbons next door to each other. Let's look at some examples. Here are two examples, one with OSO4 and one with HiO4. See what you can do. In our first example, the fact we're starting with an alkene and we have OSO4 tells us that we're going to make a diol. It's going to have the same structural features as the starting material. The only difference is that we're going to add a pair of OHs. And since we do have a situation where we can observe the stereochemistry, it's worth noting that those alcohol groups are going to be cis to each other, which is creating, in this case, a single stereoisomer, because although we have a pair of chiral centers, our compound is actually meso. But the more important thing here is that we get that stereochemistry right. And even more important than that is that we break that pi bond and we put an OH on each of the carbons that was involved. In our second example, we are looking for a pair of alcohol groups that are on adjacent carbons. So notice that the alcohol group on the left-hand side is attached to a carbon that has no alcohol group next door to it, so that alcohol will not react. However, the two other alcohol groups here and here are on carbons that are adjacent to each other. So we'll make one a circle and one a triangle, and so we're going to cleave the bond in between those and get two independent fragments, one still containing the original alcohol group, and we'll turn that other alcohol on the square carbon into an aldehyde. Since it was secondary, it had a hydrogen attached originally, as did the other one, and so the triangle carbon will also turn into an aldehyde, and these will be two separate molecules. And notice again that one alcohol group remained intact because it had no second OH adjacent to it. The two OHs that were vicinal or 1,2 to each other were oxidized, and the carbon-carbon bond that was originally between them broken.